So I want to talk today about my favorite IBL activity, and that is creating course notes for IBL courses in collaboration with my students and my colleagues. And so what I want to do is tell you a bit about how I do that and give you some specific examples, and in the end invite you to join the collaboration. So to start out, I have general strategy for how I like to do this. And I usually do it in 3 steps, in 5 steps. So in creating course notes, the first thing I want to do is I want to conceive of a course that students need that isn't available, and to figure out what the goals should be and what the strategy should be for achieving those goals. And I'm going to give you some examples of this. But the next thing I do, once I'm clear on what the course should be, is I sit down and I write a draft of a problem theorem sequence, whatever is appropriate for that course. I try to just do that as a first draft of a sequence that will achieve the goals that I want. Well, my first drafts are very much first drafts, and now comes the real work of testing them with students. And so what I'll do then is take the rough draft of the problem theorem sequence and work through it with a class of students. And as I do that, I learn an awful lot. I see what works for the students and what doesn't work for them and what they need, and take a lot of notes along the way. And then at the end, I will, after the course is over, I will write a revised version of the notes that will often look quite different than the original one. And I'll do that several times until I'm feeling satisfied with them, that they are achieving what I wanted and working well for my students. And once I've done that, then I'll have colleagues beta test the course. And so this is where the collaboration is with colleagues. Colleagues at my institution or elsewhere will teach from the notes and give me feedback, and I'll take that feedback, and that will feed into further iterations and revisions until I'm satisfied that I have just what I need and what works well with the students. And when I've done that, then I'll publish the notes and make them available to anyone who wants to use them. And so I've done this a number of times. I've written a number of different sets of course notes for IBL courses, and I'm going to mention a few of them and then zoom in and give you some details about how this process works with a couple of specific ones. I have written 4 sets of course notes this way that are published in the Journal of Inquiry-Based Learning in Mathematics and have been used now by quite a number of people. I have my Euclidean geometry notes that were published by the MSRI and American Math Society as a book a couple of years ago. And I have 4 more sets of course notes that I'm working on and are still in the beta testing stage. So they're available to be beta tested by anyone who would like to teach a course on these. Foundations of Algebra is a first course in theorem proving that leads into abstract algebra. Language and Machines is a course for computer science and computer engineering students. Discrete Mathematics, I'm co-authoring with Ted Mahavier, and that has a long history. And I'm currently working on notes on real analysis. And so I want to focus now, to give you an idea of how this process works, focus on 2 of these, the Euclidean geometry notes and the real analysis notes. And I want to talk about these 2 because they both come out of a similar set of goals and strategies. And they come out of this idea that if you look at K-12 mathematics, an awful lot of K-12 mathematics is about geometry and about the number line. Those two topics permeate K-12 mathematics. And when I look at what students get from studying those topics in K-12, what I see is they come out with some knowledge of those subjects, but with some really glaring questions that never get asked along the way that really need to be answered in order to really understand this subject. And so it seems to me that if nothing else, when they come to college, we should help them recognize and answer these questions. This is particularly true for secondary pre-service school teachers who need to understand the subject they're teaching at a greater depth than they will teach it themselves. And so I'll speak about both of these, briefly about the geometry and more detail about the analysis. The Euclidean geometry course notes culminated in my book that's in display in the lobby here. And this is an example of very thorough application of the 5-point process that I described, which was supported by Harry Lucas and the EAF, and made it possible to do a really thorough job and get some really refined notes. The beta testing process was particularly rigorous. These were beta tested by 24 instructors in 49 classes to 947 students over a span of about 4 years. Well, I think that by the end it was hard to find anything that needed to be changed. So that we can't always do that, but that's sort of an example of what can be achieved if you take this seriously. And when you look at geometry, and look at the geometry that's taught in high school, the one overwhelming question that I think students need to ask is, well, they look at all these facts about geometry that they were taught, and what they need to know is, why are those true? Why should I believe those? Well, they're true for a reason. They can be derived in a way from axioms in a systematic way so that they themselves see why they're true. And so that's what this course does. So I'd like to go on to the analysis. The analysis course actually came out, or perhaps in a way was initiated by a conversation I had with Alan Tucker, who came to New Paltz as an external examiner for our program, and I talked to him about our curriculum. And one thing he said is that an awful lot of schools that teach pre-service teachers have removed the real analysis requirement from the curriculum. And he was advocating that we do that too. And the idea was that, well, real analysis is just too advanced and abstract for pre-service teachers. And I really wasn't uncomfortable with that, because I think it's about what they need to know. But I think there was some validity in perhaps the way it is usually taught, that it isn't very helpful to anyone. So what I wanted is to create course notes for real analysis that focus on what I see as the glaring questions that K-12 mathematics raises about the number line and functions on the number line, and then build the course around an IBL approach to answering those questions. And so I'm going to give you a little more detail about what that consisted of. So here are some questions about high school mathematics, particularly having to do with the numbers, that I can bring to my students. Here's a question: what is the square root of 17? So I ask my students on the first day, what is the square root of 17? And they say, well, that's the number you square to get 17. And I say, okay, but is there a number you can square to get 17? Now, it's a very simple matter to use the fundamental theorem of arithmetic to see that there's no rational number whose square is 17. That's very easy. So then I say, well, is there some number whose square is 17? Is there some reason I should believe that? How do we know that? And they have no idea. And, and this is something that we get along the way, essentially coming from the completeness axiom. The completeness axiom for the numbers gives us what we need to show there is a number whose square is 17. Here's another question. What is the arc sine of 0.73? Well, that's supposed to be the number whose sine is 0.73. So they know that, and so what do I ask them? Well, is there a number whose sine is 0.73? Again, they don't know, and well, where do you get this from? Well, in order to get it, what you need is to know that the sine function is continuous, and then you need the intermediate value theorem. And from that, you find out there is a number whose sine is 0.73. And so these questions are leading to the topics that we need to study. Here's one. What is the log base 10 of 41? Well, they know it's the power you raise 10 to get 41. So we ask the same question. Is there a power you can raise 10 to get 41? And again, from the fundamental theorem of arithmetic, you see very quickly that a rational number won't do that. And so then we have to wonder, well, is there such a number? And in order to answer that question, you're looking at powers of 10. Well, what you need to study then are exponential functions. Now, exponential functions come up in high school mathematics, and if you have the exponential functions, you can use them to get the log. So, but when you talk about the exponential functions, now you immediately get more questions. What is 10 to the pi power? Now, if you want to define exponents, well, it's easy to define integer exponents, positive integer exponents, negative integer exponents, and then rational exponents. But how do you define an irrational exponent? And again, they don't have a clue. They tell me that, well, if I find a number close to pi, a rational number close to pi, then 10 to that number should be close to 10 to the pi. Well, yeah, that doesn't answer the question, though. Is there a number, power, well, what is 10 to the pi? And in order to answer that, we can do that by turning this around and defining natural log first from calculus using an integral, and then use the natural log to define exponents and powers of e, and then powers of other positive numbers. So that brings in calculus and the natural log. And so the last question, I can ask a lot of questions like this, but here's another sort of different question. And this is a question that they feel good about because they can answer it. What is the integral from 0 to 3 of x squared dx? And that's a question that I can be fairly confident on the first day of class that every student can answer. And they will tell me, well, you find the antiderivative, x cubed over 3 of x squared, and then you do this computation and you get 9, and that's the answer. And I say, okay, yeah, that sounds right, but then I say, doesn't the integral have something to do with area? And they say, oh yeah, that's the area under the graph of x squared. And then I ask, well, what does the antiderivative have to do with the integral under the area? And they're stumped again. And they really don't know. That may have gone by in freshman calculus, but quickly, and was never mentioned again. And a lot of them will come out of freshman calculus thinking that that's the definition of the integral. And So what we need to do is prove the fundamental theorem of calculus. And so here you have in these parenthetical topics the topics that we need to go through in a real analysis course. But I try to do it in a way that is oriented around answering these questions. And so I want to do just that. I'm not going to be overly ambitious, but I want to do just that. And so to zoom in a little bit more, let me show you just how I go about putting together some of these details. And I'll focus now on the fundamental theorem of calculus. So what I want is some course notes that they can go through to prove the fundamental theorem of calculus. And this will be a way to understand calculus, but in this narrow way that we're going to just make a beeline toward the fundamental theorem. And so the way I've done it, and there's variations on how you might do this, but the fundamental theorem can be proven if you have two other theorems. You want to look at the integral of little f, and so you define capital F to be the partial integral function, and then you prove a theorem that says the derivative of the capital F is little f. And the other fact you need is that if two functions have the same derivative, then they differ by a constant. And now you put those two together and you get the fundamental theorem of calculus. So now we need to prove each of these, and so we go backwards. And on the right there, I'm looking at theorems that just involve derivatives. This first one from the theorem that says that if the derivative of a function is 0 on a closed interval, then it's constant. And you get that from the mean value theorem for derivatives. And you get that from Rolle's theorem. And you get Rolle's theorem from showing that a differentiable function is continuous, and the min-max theorem that says that a continuous function has a maximum minimum on a closed interval. Now, this last one is a theorem just about continuous functions. And that comes from the theorem that says that a function that's continuous on a closed interval is uniformly continuous. And that comes from the Heine-Borel covering theorem, which then comes directly from the completeness axiom. And so there's all the pieces I need over on that side. And on the other side, we need to find out something about integrals. To prove this theorem, you need this additive property of integrals, the mean value theorem for integrals, and both of those come from proving that a continuous function on a closed interval is integrable. And the mean value theorem for integrals you get from the completeness axiom to prove the intermediate value theorem, and then that to prove the mean value theorem. And this theorem on the left, the continuous function is integrable, uses the completeness axiom and theorem that every lower sum is less than or equal to every upper sum, which comes from knowing that if Q is a refinement of the partition P, then it gives you bigger upper sums and lesser lower sums. And if you put that all together, you get the fundamental theorem of calculus. So this is sort of my outline of my first outline of the theorem sequence for this part of the course. And then as I go through it, I start adding lemmas. As I go through it with students, I see where they need help, and I add lemmas as they seem to need them. And eventually, there's a bunch of lemmas, which I didn't state here. And lemmas can come up in lots of different ways. Like sometimes I'll have a student put up a proof of something, and they'll put up the proof, and we'll look at it, and we'll discover that, well, somewhere in the proof, the student assumed something that they didn't have. And the student looks discouraged and goes and sits down, and then I say, well, but then that's actually, you have proven something. You just add that hypothesis, and now you have a lemma. That if that thing you assumed is true, then the conclusion is true. And now we can see if we can use that lemma to finish the theorem. And so we get lots of lemmas coming up in that way. And so this is a collaborative process with the students to fill that all out. And so this is typical of how these courses sequences are developed. And here's just a brief table of contents of the whole thing. And so, let's see. Often I'll start here with, in Chapter 2, looking at limit points and sequences and getting down a few definitions and having them start proving things, and then we realize, well, we need to know what we can assume and what we can't assume, and so we'll go back and write down some axioms for a number line. And the axioms that I write down are the axioms for a Archimedean ordered field, which are all familiar to them, even if they haven't seen some stated as such. And then we look at the rational number line, which is the minimal number line, and look at properties of that, and look at what's missing from the rational number line, and then use the fundamental theorem of arithmetic to show certain things are missing, and then go on to try to see how they can be filled in, and that leads to the completeness axiom in the real number line. And then continuity and calculus and exponential and log functions follow from that. So that's just a brief overview and some examples of how I like to create course notes. And this analysis sequence is now in the beta testing form, so I'm looking for other people who might like to try it. Okay, and let me just end with a quote you might have heard. R.L. Moore didn't leave us with a lot of quotes, but this one made an impression. The student who is taught best, who is told the least. And I think that this is a good idea as long as it's applied judiciously. If I applied this too strictly to my students, I'd have a lot of very discouraged students who wouldn't do anything. And so I have a alternate version of this statement. And this is what I'd say. A student is taught the best who is told only enough to ensure that he or she will continue to work hard, stay engaged, and make progress. Okay, so thank you.
First of all, I congratulate you for your, over time, for your great contribution to humanity in organizing this stuff. And I have just one request to add to it. Riemannian geometry.
Oh, okay.
Okay? You agree?
Sounds good. It probably won't fit into this course.
Yeah, Harry Lucas, retired. It's been 50 years since I've been in the classroom, and I'm not a practicing mathematician. However, as a matter of historical comment, what R.L. Moore did in 624, the course after calculus, and I think now somebody should maybe try to apply this in high school. He assumed the plane, just a flat sheet. He assumed the coordinates, and then he drew S1 and S2 onto the line so that every point of S1 is to the left of every point of S2. Every point of the line is either in S1 or S2. And every point of S2, if S1 and S2 are on L. And he completed the completeness axiom with a dead cut statement, but he didn't mention any words or any jargon, and you can just visualize that. Now, I'm one who likes to visualize, and I think a lot of our difficulty is that new students are visual more than they are jargon-oriented. And if you could put a few graphs and some pictures into your notes, maybe they would start visualizing these things, and you can prove every theorem in calculus from that simple deal, assuming the plane. Just a comment. Thank you.
Yeah, I think that's a very good comment, and I intend to do that.
I was just saying, I thought it was really exciting that you started. Oh, I'm Elizabeth Thorin. I'm from UCSB. But I thought it was really cool that you started these big theorems from very simple questions that were really approachable. And I'm wondering, are you starting like new sections with this really simple question, or is this just day one, we look at these questions and now we start to say, how can we answer them?
Yeah, no, I'll start each section with a question like that.
Okay, and then, yeah, so do students ever start to conjecture the big theorems because it's like the thing they need to answer the question?
Yeah, I try to get that to happen.
Yeah.
And sometimes they do and sometimes they don't, but yes.
No, that's
certainly part of what we want to do, yeah.
No, it's something I try to do too, but yeah, I understand it's not easy.
Yes, yes.
Robert Vallon, I might have missed this, but is this a one-semester course or a two-semester?
2-semester course, yes.
Any other questions? No? Okay. Thank you all. I believe we have a few minutes before our next talk, and if we could thank David again, I would appreciate it.